Our next topic is natural logarithmic functions, section 8.5, and we have three objectives. One is to find logarithms or powers to base e using a calculator, and then change your base formula to find logarithms with bases other than e or 10, the common logarithms, and then graphing exponential functions and logarithmic functions base e. We begin with the base e in natural logarithms, and so it's based on the number e, a transcendental number, e equals 2.71828, etc. It's an irrational number. It's a non-ending, non-repeating decimal. And so logarithms base e are called natural logarithms or Naperian logarithms in honor of John Napier, who lived from 1550 to 1617, a Scotsman who invented logarithms. So he came up with that idea. So the abbreviation ln is commonly used with natural logarithms. So the ln of 29 means log base e of 29. We generally read ln 29 as the natural log of 29 or simply ln of 29. So these expressions are equivalent. They can say the natural log of 29 or simply ln of 29. And as before with other bases, the natural logarithm of 1 is equal to 0, and the natural logarithm of e is equal to 1 for the logarithmic base e, and where e is the number up here, the irrational number. The next three exercises are about finding the natural logarithm to 4 decimal places of some numbers, and that, of course, for that we we use a calculator, 78,235.4. So I enter that into the calculator, and then I press the ln key, and so here's the answer, 11.2675 when we round it to 4 decimal places. So 11.2675. And similarly, we look up the other natural logs of these numbers. So the natural log of 0.000309 is minus 10.3848. And the natural log of minus 3, of course, does not exist. Remember that the logs are only we can only compute logs of positive real numbers. Does not exist as a real number. And the log of 0, of course, does not exist either. Does not exist. And the natural log of 10 is 2.3026. And then to find e to the 11.2675, so we input the number 11.2675 and then raise it to the e to the x power. So we input the number and then press the e to the x key. And here's the answer, 78,237.4 0.1596, rounded to 4 decimals. And we find e to the minus second a similar way, and so that answer is 0.1353. Next is an important topic for working with logarithms. So it's an important formula, you want to keep that handy. For any logarithm bases a and b in any positive number m, the log base b of m is the log base a of m divided by the log base a of b. So it's a very important relationship because it's sometimes desirable or important to change bases for logarithms, and this is how the formula works. So here we have an example. Find the log base 6 of 7 using common logarithms. In other words, logarithms base 10. So in other words, the log base 6 of 7, to change bases to the common logarithms, would be the log of 7 divided by the log of 6. So the log of 7 is approximately 0.85098. Of course, we rounded it up, and then the log of 6 is approximately 0.77815. And so then the quotient is about 1.0860. So that's changing to finding log base 6 of 7 using common logarithms. Similarly, when we are asked to find the log of base 6 of 7 using natural logarithms, of course it's the same. It's a natural log of 7 divided by a natural log of 6, and that's approximately equal to the following. So that's approximately equal to 1.945910 divided by 1.791759, and of course the ratio will be the same, approximately 1.0860. In a similar way, we can find log base 2 of 46 by writing this way. Log base 2 of 46, and we're supposed to use natural logarithm, so it'd be the ln of 46 divided by the ln of 2, which is approximately equal to 3.828641 divided by 0.693147, and so that's approximately equal to 5.5236. Next, we'll be looking at some graphs of exponential functions and logarithmic functions base e. So the first exercise is graphing f of x equals e to the 2x. So I made a table of selected values of x, and I computed the function values using my calculator, of course. So when x equals 0, then the function is equal to 1, etc. So here's the ordered pairs 0, 1, 1, 7.39, and x equals 1/2. Then the function is 2.72. These numbers, of course, are approximate numbers. They're rounded. They're not exact numbers. because when you raise e to any power, you have, again, a irrational number, except for x equals 0. So here are the ordered pairs. We're going to mark them on the graph, and then we connect the points, the ordered pairs, with a smooth line. So here's the plot of the ordered pairs. And here's the completed graph of f of x equals e to the 2x. It's a rapidly rising function, and this is what the graph looks like. In a similar way, we graph the function g of x equals 1/2 e to the minus x. We select some values for x, and then compute the corresponding functional values. And except for the first one, all of these are really approximations, because these numbers are really irrational numbers. But here we have the ordered pairs, and so we're going to plot the ordered pairs on the graph and then connect the dots with a smooth line. So here we have the plotted the ordered pairs, and here's a completed graph of g of x equals 1/2 e to the minus x. Next, we're going to graph some functions of the natural logarithm of x. So here f of x equals 2 times ln x. So we select some values for x, compute the functional value, and then we have the ordered pairs. And then we plot the ordered pairs, and then we connect those ordered pairs with a smooth line. So here we have some ordered pairs, and here I plotted the ordered pairs, and now we're going to connect these dots, and that gives us the graph of the function. This is the graph of f of x equals 2 times the natural log of x. The next exercise is graphing g of x equals the natural log of x minus 2. And again, we select some values for x, we compute the corresponding functional values, we get the ordered pairs, we plot the ordered pairs, and then we connect those dots with a smooth line. So here we have 5 ordered pairs, and here are the plots of the ordered pairs, and now we will connect them with a smooth line, and that'll be our graph of g of x. And this is the completed graph of g of x equals ln of x minus 2. And this is this concludes section 8.5.